Hey there everybody, hope that you're all doing well. So I wanted to make this video for you guys, introductory video, on this concept in biology that is referred to as signal transduction. And this is a pretty popular concept that a lot of students in high school, most likely in their AP biology courses or physiology, a lot of students in introductory biology courses will be reintroduced or introduced for a first time to this concept. And a lot of times people that I've come across and during my time in college had a lot of trouble understanding this stuff. And so I provided a couple of illustrations here over on my right hand side that I'm hoping will help give you a more thorough understanding into what signal transduction is and how you can learn to apply it to what I'm assuming many of you are doing, which is probably a pre-health career, like doctor, nurse, veterinarian, etc. And so, let's get started. So the first question that I want to ask you guys is what? What in the heck is signal transduction? Well, signal transduction is, and I'm going to throw some jargon out there because I'm assuming those of you watching this do have a background in biology and chemistry. So signal transduction is basically when you take this extracellular chemical messenger, usually in the form of some sort of molecule, what we refer to as a ligand in a chemical reaction. And what's going to happen is this extracellular messenger is going to activate this, it's going to activate a particular receptor on the cell membrane. And when that happens, it's going to trigger a biochemical pathway within the cell. And when it triggers this biochemical pathway inside of the cell, that's going to cause a series of pathways to go off. And more specifically, I want to use this term that I think will better help elucidate what I mean by pathway. It's basically going to go to cause this chain reaction. And what I want to do here is, before I get into any more ideas behind signal transduction, I want to take this biochemical definition of signal transduction and apply it on a real-world basis. So let's take this picture over here. Looks like a pretty weird picture. Well, this weird-looking picture over here is what is defined as a Rube Goldberg machine. And for those of you who aren't familiar with what a Rube Goldberg machine is, it's named after a gentleman who in the early 1900s, by the name of, you guessed it, Rube Goldberg, he was a cartoonist and inventor who developed these super overly elaborate and complicated mechanisms that allowed for the simplest of tasks to be performed. And as we can see with today's comic strip, this one is defined as being a self-operating napkin. And what happens here is, as soon as the gentleman lifts up his spoon, we're going to go through a series of complicated reactions that will eventually end with this napkin wiping his face so that he can have a nice clean mustache. And according to Webster's dictionary, a Rube Goldberg machine is specifically defined as a machine that accomplishes, so I want to write this down because I think it's a good definition, machine that accomplishes something simple through a complicated means. Now, the reason that I'm putting this definition down, the reason that I've even bothered to mention this Rube Goldberg machine, is because this is an exact illustration that explains exactly what's going on at the cellular level. Again, at the cellular level in biology, we have a complicated series of biochemical reactions, or this chain reaction, that is usually going to accomplish a pretty simple task. And so if we extend upon this idea of a Rube Goldberg machine, I want to take an example. Before I go into the picture on the right, I want to take an example using my own cell contraption. So, keep the color going there. So what I want to do here is let's go ahead and take our beautiful cell here and put a cell membrane receptor. Just as I said before, we're going to have this extracellular messenger. Let's take this yellow dot here. No, you know, we already have yellow. Let's use this color right here. So we have this picture right here. This will be our chemical messenger. And what it's going to do is it's going to bind to our protein receptor. You know what, let me take the appropriate color for the protein receptor. Nope. And when it binds, can't get the color. And when it binds to our protein receptor, as I said, it's going to set off a series of chain reaction biochemical pathways inside the body. And so if we take each of these dots here, you know, these dots are going to represent protein complexes that are going to be triggered as soon as this chemical messenger and this protein receptor bind together. And as we see in this picture over here to our right, that's exactly what's going on. We have this ligand, or as it's called, a primary messenger, binding to this cell surface receptor to form a receptor-ligand binding interaction. And when that happens, we're going to have these intracellular secondary messengers going through, transmitting a signal, or transducing a signal, if you find it easier to use the literal term, that will eventually allow for, in some cases, a change in gene expression. So let's elaborate upon that a little bit. So as soon as we have the receptor-ligand binding complex occur, we're going to have each of these protein complexes being set off in this chain-like reaction, just like we had in our Rube Goldberg machine. You know, we had one part being set off all the way until we got to the end, and by the time we got through this complicated means, we were able to accomplish something that's a little more simple. And so what's going to happen at the very end is, as soon as we get to the nucleus region of our cell, assuming this is a eukaryotic cell, we know that we're going to have DNA. And what's going to happen is one of the protein complexes within our cell is going to bind to the DNA. And when it does that, it's going to, as I showed in this drawing over here, cause a change in gene expression. And another way to understand that concept is basically what's going to happen is we're going to get this brand new protein. So I'll go ahead and label that. And this brand new protein, well, you know, it has a couple options of what it can do once it's been synthesized. And the options that it has is it can either stay in the cell and go to carry out intracellular biochemical processes that the cell perhaps needs, or the other option, it leaves the cell. You know, maybe the cell is fine without this protein being present, and so what will happen is this protein can then exit the cell and go help out another cell, accomplish another task, just like this one. So I want to go ahead and leave it right there. I think that's a reasonable place to stop for an introduction into signal transduction. And what I'm hoping to do in the next example, as well, what I'm hoping to do in the next set of videos is I'm going to focus on signal transduction within the human body, because, as I said in the beginning, I assume most of you, you know, unless you're doing veterinarian or animal care, you're going to be working with human bodies, and you know, it's important that you begin to learn the biochemistry behind how these human bodies work and how they're able to accomplish the tasks that they are. And so in the next video, I'm going to address a specific example of how transduction occurs in the human body and how we can learn to apply that knowledge to attain a successful understanding of signal transduction and how it works and how we can use it to our advantage. So I hope you enjoyed that introductory video, and I'll see you in the next video. Take care, you guys.